Thank you, Elizabeth. Also, thank you, Trevor, for having me here, for inviting me, and providing the possibility to present these results. I'm going to report and discuss experimental result of a small angle neutron scattering experiment on a neodymium iron boron magnet. That is an experiment that we have carried out at the SUNS instrument of the reactor at the Japan Atomic Energy Agency. And also I will show results of micromagnetic simulations on nanoparticles. That's where the nano from title comes from, because usually neodymium iron boron magnets, the commercial ones at least, they are micron scale. But before we come to the results, let me thank a few people. So my group in Luxembourg, Evelyn, who also joins us online, who carried out the micromagnetic simulations on the nanoparticles. Then also partially Michael, who was here at Links, had a 3 months stay with Elizabeth. Then my former postdoc, Matthias, who carried out the experiments together with Andreas Michels in Japan at SUNS instrument, and also like to acknowledge Konstantin Medlov from Donetsk for continued theoretical support. So the motivation for this talk, for this study, dates back to a paper from 2014, where we have reported this angular anisotropy on a two-dimensional detector. So this is a neodymium iron boron magnet, the same magnet that will report let's say the newer results, the latest results. So here what we have observed is this angular anisotropy. Here we see along this horizontal direction here, we see what we call a spike. So that is known as a spike anisotropy. So you have an isotropic part, and then you have this peculiar feature here along the horizontal direction. And that has been reported 2014, and already in 1999, long time ago, this feature has been theoretically predicted using micromagnetic theory. So here you can see this is an analytical result, and we know the origin of this feature here in the cross section is the magnetodipolar interaction. So if you leave out the magnetodipolar interaction in the calculation, then what you get is just something isotropic. Yeah, you will not get these peaks here. So we know origin of this is magnetodipolar interaction. This is there, it's operative. The question is, of course, then the next question that comes: what is the underlying spin structure? So what in real space? How are the spins arranged in real space in order to see such an angular anisotropy? And then for some years we stopped with that topic, and then I think in 2018 Ichiro Oba, he came to my group to Luxembourg. He's an instrument scientist there in Japan, and then we discussed the data, and then he suggested to redo an experiment with an extended magnetic field range and extended momentum transfer range, and that's what we did, and the results are going to be reported today. This is a brief outlook, so a little bit on magnetic small angle neutron scattering, then the experimental results, and then I will give you a summary conclusion. So that's the setup that we typically use. You have the sample here, incoming beam, then you have a two-dimensional detector behind it. The scattering angles typically is a small one, is below 10 degrees. The wavelengths here that we use is in the 5 to 20 angstrom regime. And then if you insert all these numbers here into the elastic expression for the scattering vector, then this translates into 10 to the -2 to roughly 5 nanometer to the -1. And so this is let's say, in real space, that's a scale of the order of a few nanometers, let's say up to 100 or 200 nanometers. In general, if you use similar setups and you use techniques known as very small angle neutron scattering or ultra small angle neutron scattering, then you can even reach the micron scale with this technique. Important is also, what is additionally important to mention is that with this small angle scattering technique, of course, as with any neutron technique, we measure nuclear scattering and magnetic scattering. So it's measured in transmission. So we really get the bulk information, and the wavelengths that we use here above 5 angstrom typically is above the so-called Bragg cutoff. So we are not measuring lattice constant. We're not sensitive to to structure on a scale of really angstroms. So we're not measuring atomic magnetic moments. We are sensitive to what I call the mesoscopic scale. So above typically unit cell sizes of common materials. Again, here is the length scale is written. Then the outcome of an experiment, you get these type of two-dimensional scattering maps. Show here a few for different materials. This is the iron-based two-phase alloy. So you see here a kind of a clover leaf type angular anisotropy of maxima here roughly along the detector diagonals. This is due to the two-phase nature of this sample here. You have iron particles in a magnetic matrix, so there's a jump in the saturation magnetization, which gives rise to a dipole, and then that dipole imprints its structure here in the scattering pattern. That's the spike anisotropy that we will discuss in a while. Here you have a few other results on iron-based alloys. That's typical scattering pattern at the saturation. That's non-spin flip scattering. That's the scattering of in the spin flip channel at saturation. You see sine square, cosine square signature. And that is also a particular anisotropy that you observe in saturation in these alloys when the ratio of nuclear to magnetic scattering takes on a certain value. Okay, so for small angle scattering, the relevant quantity for magnetic small angle scattering, that's what I'm talking about. The relevant quantity is not the individual atomic discrete moment, but the magnetization vector field, which is generally a function of the position, x, y, z in the material, and of course you can also include time in this picture here. So we have what we are sensitive to here are spatial variations in this vector field. Here you can see this on this sketch here on a scale of a few nanometers up to a few hundreds of nanometers. So in one region, let's say the moments they point, the magnetic moment, the magnetization points into a certain direction, and then over a length scale of a few nanometers or tens of nanometers, the direction of the magnetization here changes. Also, you can see when you go from here magenta color to blue color, the length of the vector may change. The length of the vector stands here for the magnitude of magnetization. So whenever you have these two things happening, that the magnitude of the magnetization changes on the nanoscale, or that the orientation of the magnetization vector changes on this mesoscale, then that this is a contrast for magnetic small angle neutron scattering, and then you get a sun signal. Also, one comment, because a question that I get quite often. I mean, magnetism is of course a purely quantum mechanical phenomenon. Why are you not, let's say, tackling that within a quantum mechanical approach? The answer is simply when you do this really strictly, when you do the calculations, the modeling strictly quantum mechanically, that is numerically simply impossible to do. I mean, the Hilbert space is extremely large, or becomes extremely large for purely quantum mechanical calculations. So what we do is our micromagnetic continuum calculations. That's what we use in order to understand small angle scattering. Here again, I wrote this magnetization vector field. So it's a Cartesian vector field in Cartesian coordinates here. Each component depends on the position in the material, and within this approach, this is assumed to be a smooth and continuous magnetization vector field. So you don't have like, for instance, in an antiferromagnet, where on an atomic scale of a few angstroms, you have quite large chunks in the orientation of the magnetization by 180 degrees from one lattice to one sublattice to the other. Here you have a very gradual, a very smooth change in the orientation of the spin. And also this whole theory is subject to the constraint that the magnitude of this vector field is a constant. This is simply the spontaneous magnetization, which you can see here, which varies as a function of temperature, but that's only a function of temperature. So this is the constraint, the condition here. And you can also see that this condition implies that actually only 2 out of these 3 components are independent. This is a kind of a, can build this in as a kind of a Lagrangian multiplier, and it implies, as I said, only 2 out of the 3 components are independent. If you know what is MS, then the other one is determined. That's in this flowchart. You can see our approach. So we start with an energy expression with a micromagnetic Hamiltonian. Everything is purely semi-classical. We carry out the micromagnetic simulation. We get the magnetization field in real space, Fourier transform it, and then get the magnetic Sun's cross-section. So here I have written down the expressions, the main expressions that are relevant in this micromagnetic theory. The first one is the Zeeman energy. Of course, you apply a field, you rotate the moment along the field. Then you have the magnetostatic energy. That's this term here. That's actually the central one in my talk, and it's actually the most complicated one. Then you have the different expressions for the magnetocrystalline anisotropy. So the material that you study has a certain underlying crystal lattice, can be cubic, can be hexagonal, tetragonal, whatever, and that implies that you have a certain magnetocrystalline anisotropy energy. In this case, I assumed it to be of cubic type. Then you have an exchange interaction. This is this expression here. This is just a continuum form of a quantum mechanical exchange interaction. The exchange interaction is a quantum mechanical origin. It tries to orient the spins into a parallel direction, and that's the continuum formulation, from where you can see that this is a positive constant, so any kind of gradient, any kind of inhomogeneity in the magnetization distribution goes along with an energy increase, and that is the Dzierżynski-Moria interaction, which I'm not going to discuss in this talk. Actually, as I said, this here, the magnetodipolar interaction or magnetostatic interaction, this ED, it looks, as it is written here, very simple, but it's actually the most complicated, because this magnetostatic field itself depends on the magnetization. So the magnetization is the quantity that you want to calculate. So actually, this HD is given. For this HD, you have to write down another integral, so that actually the energy that you need to calculate is a six-fold integral. You have to integrate twice here over the same volume, which makes this expression here non-local, and it's usually the most difficult one to treat in these calculations here. So and then of course when you calculate now the magnetization vector field, you calculate the Fourier transform and then the cross section. This is the well-known expression for the elastic magnetic neutron scattering cross section. So what we measure here, the cross section is simply given by the Fourier transform of a quantity known as the Halpern-Johnson vector. Not going here into detail, but essentially what you see here, this cross section, you have here a sum. This is just a constant. And then you have here the sum. Alpha beta denotes Cartesian coordinate indices, so it's x, y, or z. And then this here, this is this Kronecker function, and so on. This is just a trigonometric function. This is just a sine or cosine. And here you have simply the Fourier transform of the Cartesian components of the magnetization. And then you can calculate it, you can plot it, and you can analyze it and compare it to your experimental data. So now let's discuss the experimental results. So that's what I have shown at the beginning. Yeah. So this is the experimental result, and we know already that the origin of that anisotropy here is the dipolar interaction. So it's due to these non-zero divergences of the magnetization. So you may know or not know that from your magnetism or electromagnetism lectures, that the origin of the magnetostatic energy of is related to so-called magnetic charges, magnetic surface charges. So whenever you have a discontinuity in the magnetization of the material, so you have a macroscopic magnet, and let's say if this magnet is fully magnetized, then at the surface, at the outer surface, the magnetization jumps to zero, and that is a discontinuity. And at that surface, you have, this is the origin of a magnetostatic field. Yeah, that's what typically this is known as the stray field. So you can think of it that the stray field, let's say, emerges from the surface. And that was, let's say, for the case when you have a homogeneous material, everything is homogeneously magnetized, because in that case, the divergence of the magnetization is zero in the bulk. If the material is not homogeneously magnetized, then the divergences of the magnetization within the volume of the material, they may not be zero, and they may cause themselves a magnetostatic field. And that's the origin of this. As I said, we have understood it. Question is, of course, what, as I said at the beginning, what is the real space structure? This is all in Fourier space. And then we did this experiment in Japan with an extended field range here. and also an extended Q range here. So this is the experimental data. We see here, this is already averaged. You see here kind of a Guinea type behavior. Then you have a power law here, which is due to the -4. This is magnetic scattering. It's all unpolarized scattering, so no polarization analysis or so. And also here you see this exponent here, which deviates from what you may know as the Pogod law, which is, I would say, in magnetism, you find this relatively often. In particular, for inhomogeneously magnetized materials, you find it's quite common to find exponents here that are larger than this exponent of 4. So then what we did in order to get information in real space, we have Fourier transformed again the data. So first we calculated it in real space, I mean, at least in the simulation, and then we Fourier transformed it, and then we went back again. So here we Fourier transformed the experimental data. That's what we have done here, yeah. And then we plot here this correlation function, and that we plot here the function P of R. These are just different representations of the same physics here. So this C of R here is simply here the integral without the R square factor, yeah. And then the P of R, which is, let's say, in nuclear small angle scattering, and in Sachs is usually quantity that people prefer to discuss, that is drawn here. This R square factor here, of course, has as a consequence that here P of R is 0 and R equals 0. And of course, the R square factor also, it emphasizes features in C of R at medium and longer range distances here. Yeah? So what we see here is we see here that the experimental or the P of R that we get from the experimental data has somewhere here a 0 crossing here. Yeah. So at this particular value here has a 0 crossing, and then here it approaches here again 0. This the dashed line is something that we would get for a homogeneously magnetized spherical volume. This 0 here, this 0 crossing, you can also see it here in the C of R data, but it's less pronounced due to this R square factor that I mentioned. So the question is, we measured that and we found that, and then the question was, okay, we have this 0 crossing here. What could it be? What is the origin of that 0 crossing? How can we interpret that? How we can relate it to a real space spin structure? And then we can make use, or we made use of a result of my former postdoc Laura Vivas, and of also Evelyn, my PhD student who joins us online. She carried out micromagnetic continuum simulations on nanoparticles, so quite a different thing. The result, just to remind you, was on a neodymium magnet, really a bulk material, micron-sized features, at least in the structure, not in the magnetic structure, but in the real, in the nuclear microstructure. And these results, or these simulations, they were carried out on nanoparticles, on iron nanoparticles, and the background of that study was a completely different one. So in short, what has been found here is when you increase the size of these iron nanoparticles, so we start from something like 10 nanometers, and then we go all the way to 100 or 200 nanometers, then we find that above about 20 nanometers, we find this type of vortex structure. This is also not, I would say, something particularly new. It has been reported before many times. But we have studied that in the context of small angle scattering. So what's the context, what's the signature of that in the small angle scattering? And we see here that in the C of R we get a 0 crossing, and in the P of R we get that. And that, of course, then we can link that, we use that to provide an idea, to provide an explanation for the experimental result that we have seen in the neodymium magnet. If we leave out in this simulation, so here we have all the energy terms that I mentioned before. If we leave out here in these simulations the dipolar interaction, then we get simply a single domain. We get Stoner-Wolford behavior. Yeah? You see also when it's saturated here at 0.5 Tesla, that's the yellow line. We recover here, this is just the correlation function of the homogeneously magnetized sphere, or here this the P of R of the homogeneously magnetized sphere. And then if you go to lower fields, at some point the vortex nucleates. And then, of course, we get the peak type feature here in the cross section. So we get the deviation here from the Guinea behavior. And here you see that this vortex here has a 0 crossing here at a value that is about the radius here of that particle. Diameter was 40 nanometer. And I mean, it's relatively easy to understand. What is shown here, the C of R, is nothing else essentially it's the autocorrelation function of that vortex. And if you just autocorrelate such a structure with itself, then of course when you have this the usual construction, you have the vortex and the ghost vortex. Initially, when they lie onto each other, you have the maximum of the correlation here, maximum overlap, and then you're shifting one with respect to the other, and then you're getting a decay of the correlations. And at some particular distance R, in one region, the spin points in that direction, and the other one points in the antiparallel direction. And that's the reason why you get a zero here, which is more pronounced here. And then what we have calculated also from this experimental data here, so from the experimental data here, we know we have the correlation function, and we extracted here now a correlation length. Yeah, and that has been done in the following way. So we have defined the correlation length as this is the first moment, LC. The correlation length is field-dependent quantity as the first moment here of this correlation function. Yeah. So this here is what we get from the simulation here, the red dots, and they are limited here by a value of 8/15 times the radius. That's the dashed line here. So that there are two different scales here. The red here, that refers to the simulations where the size was 40 nanometer, and this here is the experimental values that we get for the correlation. Yeah. Just one comment. Why do we have here different length scales? The reason is simply when you go back. When you go back to the simulations, the formation of such a vortex happens here for iron above 20 nanometer. So each material, depending on its materials parameters, has something that is known as the single domain size. Yeah. So below that size, roughly, quantum mechanical forces are so strong that they hold all the spins in parallel. You have a single domain, one single macro spin. Now you make it larger, the material, the dipolar interaction gets stronger, and then the vortex forms. For neodymium iron boron, in order to model that, because the materials parameters are such that the single domain size is on the order of 200 nanometers, one would need to go, probably in order to get a vortex here, one need to simulate a size that is approaching 1 micrometer. And that, from the numerical cost point of view, is simply, it's too expensive. It would take too long to calculate that. So there is no reason not to believe that this type of scenario happens for any type of material. That's why we have here resorted to the results here for iron, where this happens as above 20 nanometers, so it's relatively straightforward to calculate it. So we just also one word to the calculation. This is of course one single snapshot of one particular vortex, but of course in the simulation this data here is for randomly averaged particles. So we have calculated over the whole hysteresis loop, starting from saturation going to the negative saturation. We have calculated the random average for typically a few hundred different easy axis orientations of the particles, and that takes probably to generate such data, it takes of the order of 1 or 2 days. And that is simply not possible if you go to neodymium iron boron. So that's the result here for the correlation lengths. If you insert here now for C of R, how do we get this value here for the uniform sphere? I mean, the correlation function of a uniform sphere is well known. It's a formula that you can look it up. If you insert that here, and you get this value here, we see that for the simulation we get quite a very good agreement here. It's clear if you have a single, in the simulations we have a single vortex. Yeah, if you have a single vortex, then of course, it's clear that initially, when you are at low field, when the vortex is there, the correlation length takes on its smallest value. Now you apply a field, you saturate the particle, and then the correlation length increases, and that's what we see here. However, for the experimental data here, we see a different exponent. That's the phenomenological expression that we use as a power law. For the correlation length value at zero field plus this power law here, we see a different exponent. And for the moment, we tend to believe that this is due to the fact that in the simulations we have only one vortex, whereas in the material here we may have interacting vortices, and that could be the reason that we see here these different exponents. So yeah, that's basically it. Here's the brief summary. So I hope that I could convince you that the combination or the marriage of magnetic small-angular neutron scattering and micromagnetic theory is quite useful for the quantitative analysis. of magnetic materials on a mesoscopic length scale. In this particular case, the dipolar interaction is the most important interaction. It's a long-range and anisotropic interaction that must be taken into account for this understanding, for the fundamental understanding. It results in vortex-type structures. We see no Guinea law, and taking the results together, simulations, experimental results, we can suggest that, let's say, this spike anisotropy has its origin in vortex-like flux closure patterns, and of course these reduce the remnants. One maybe last thing, that the fact when you have inhomogeneously magnetized particles, that leads to what we call intrinsic spin disorder-based smearing of the sun's cross-section. This can be seen, or could maybe seen from this image here. I mean, you all know when you have small angle scattering and you have homogeneous particles, now you have homogeneous particles of different sizes, then the size distribution, of course, leads to a smearing, and you do not see any more these form factor oscillations here, you just see an envelope. But the very same thing happens here, because if you consider a random average, or let's say you consider a sample that has different magnetic particles that are differently oriented, so each particle has its own a different orientation of magnetic easy axis relative to the global direction of the external field. That means that each particle has its own energetics, own magnetic energetics, meaning has its own spin structure. If you have a distribution, or if you have 500 different particles, then you may, for given sizes, and even if the particles have the same size, so there is no particle size distribution, you find particles that have different spin distributions than other particles, and this different spin distribution leads then also to a smearing of the cross section without a particle size distribution. So when you go here from high field when it's saturated, you have single domain, you can see the peaks here, but then at zero field here, when you have these type of vortex structures here, you see that the peaks are progressively washed out. I must admit, this is not the best example here, but I have other examples here that I could maybe show you. Yeah, you can see it here. These are different spin structures here. Particles all have the same size, and then we calculated from each of these individual particles the cross section, the radially average cross section here, and then you see they all have different cross sections here, and then you see features or oscillations here. But when you average them, then all these features, these oscillations, they're getting washed out. Thank you very much for your attention.